Today I'll be presenting on my work called DisCo. DisCo is short for Disassemblers Combined. In this project, I'm combining disassemblers for improved disassembly performance. So the problem that we are trying to address in this project is about how we can disassemble malware efficiently. Firstly, we need to know the definition of disassembly. It refers to the process of converting a binary into assembly code, and in this assembly code you can look at different functions in the binary as well as the machine level instructions under each function, and most of the disassemblers also give you the call graph and control flow graph information. So the question here is really, which is the best disassembler to use for a given malware binary? Because today we know that there are lots of disassembler options available like IDAPO, Ghidra, Anger, BAP, Binary Ninja, and so on. So the other important question is also, what is the level of accuracy that we can expect from these disassemblers? So in short, these are very hard questions to answer because many disassemblers exist and not all of them have been evaluated in a systematic fashion for the various architectures. Secondly, a given malware binary can be compiled in various ways because there are so many compilation configurations available, like compilers and the options that are used to compile them. So these may actually affect the disassembler performance as well. So our solution is basically DisCo, which is short for Disassemblers Combined. So the key insight is that instead of choosing the best disassembler, we use all of them to get superior disassembly accuracy. So we are proposing DisCo, which is a systematic approach to combine collective capabilities of disassemblers, and also after doing that we conduct systematic evaluation of disassemblers and also evaluate DisCo as well. So you can think of DisCo as an AND gate, and we actually use DisCo to actually combine the disassembly capabilities of a bunch of disassemblers. Like you can look at the green AND gate in the picture. So for example, we can combine 5 disassemblers together: Anger, BAP, Ghidra, IDA Pro, and Red 2. And in our study, we found that combining all these 5 gives a disassembly accuracy of up to 99.8%, and this is a 17.8% improvement over the best disassembler among the group. So this is a very significant improvement over the best disassembler that you could have possibly chosen, okay, for the group of binaries. So overall, and of course you can actually choose a different group of disassemblers, like you can just go with the for free disassemblers, for example, and even in that case we found that there is a 12.4% improvement over the best performing disassembler. Overall, this project was a huge success because we found that DisCo can combine effectively the different disassemblers, and it can give an improvement of up to 17.8%. Not only that, DisCo can also be used to improve other disassemblers like Ghidra, for example. And in the course of our study, we have also discovered a bug in Ghidra, and we will give you more details in the following slides. So the motivation for this whole project is just that binary disassemblers continue to be crucial frontline tools in the defense and containment of malware. So if you remember, back in 2017, 2 ransomwares actually infected over 230,000 Windows machines in a span of just one day, and they have spread across 150 countries, and the total damages cost over $4 billion. So disassemblers are needed to actually study the operations of these binaries and stop them in a timely fashion. This is the roadmap for today's talk. And let's look at the background. So from previous work, we know that 66% of malware binaries belong to the ARM and the MIPS architectures. So we are focusing on these 2 architectures in this project. And malware binaries can vary by architecture, compiler, and compilation options. And actually we wanted to study how these factors affect disassembly. And in addition to all of that, we are actually focusing on the function start identification metric in disassembly. And this is because this is a fundamental disassembly metric, as has been noted in previous work. Not only that, previous works have also stated that this is the most challenging metric for disassemblers. So that is why we have chosen to focus on the function start identification metric for disassembly in this work. If we look at the previous work, in summary, no previous work has ever attempted to combine disassemblers to improve disassembly. So this is a very novel approach. And furthermore, no previous work has attempted to actually evaluate disassemblers for the MIPS architecture for malware. So there is limited previous work because no previous work has focused on using malware to do evaluation as well. Previous work usually focus on evaluating disassemblers on benign binaries, and they have found that function star identification is a challenging metric for disassemblers, and they found that IDA Pro to be the best performing disassembler so far. Two previous work that are evaluating disassemblers to find the best disassembler are an empirical study on ARM disassembly tools and also an in-depth analysis of disassembly on full-scale x86-64 binaries. There are also other works which present new techniques for more accurate disassembly, but each of these techniques have their own limitations. You can refer to these papers to know more details. In our dataset, we have a total of 1,760 IoT malware binaries which were compiled from 88 IoT malware programs in the C language, and all these binaries belong to either the ARM or the MIPS binaries, and they have been compiled with either GCC version 5.5 or Clang version 9 compiler. They have been compiled with different compilation optimization options as well. In this study, we have used a total of 6 disassemblers. They are Anger, IDA Pro, Ghidra, BAP, Raider, and Binary Ninja. Okay, in this slide, I'm sharing with you the architecture of our DisCo. So as for the input, because we want to actually combine the disassembly capabilities of different disassemblers, we have the set of disassemblers that we want to combine, and then we also have the source codes for to compile to get the binaries, and then later on we can just use an unknown binary to test the whole system. DisCo itself comprises of the module that is required for the compilation to create a ground truth so that we can evaluate these disassemblers. Not only that, we also need to create the ensemble model, which is the main part that is used to combine the inputs from the different disassemblers, and the output is of course improved disassembly. So our contribution is, there are many contributions, but the main contributions are that firstly, DisCo offers superior disassembly accuracy, because we have found that combining disassemblers leads to performance improvements of up to 17.8%. And secondly, DisCo can also be used to improve other disassemblers. For example, Ghidra. We have actually shown how we can use DisCo to improve Ghidra. The improved version of Ghidra is Ghidra Plus, and you will see in the later slides that the improvement can be up to 13.6%. So if we look at the methodology, the main method here is about how to combine these disassemblers together. And for that, we are using an ensemble model, and we have implemented the ensemble model by using a neural network. This model takes in two types of inputs or features. The first one is a binary input, and this is an input from each disassembler for each function start to indicate whether it has discovered that particular function start, yes or no, basically 1 or 0. Not only that, we have decided to include the 8 bytes before and after the function start for the MIPS architecture, and only 8 bytes after the function start for the ARM architecture due to the presence of inline data. So we feel that getting the 8 bytes around the function start is important because it gives more context to the particular function start. In this work, we are using F1 score to quantify performance, and to quantify the improvement of DisCo over the best performing disassembler, we are using this metric called relative performance improvement, RPI. So RPI is just the performance of DisCo minus the best performing disassembler for this configuration. That is the RPI. And to quantify the variability in performance during the evaluation, we are considering 5 PWC, which is the 5 percentile of worst case performance. And this value represents that 5% of the binaries for that configuration perform equal to or worse than this value, in addition to considering the average performance. This slide actually shows the overview of all the results. So we have some good news, some bad news, some ugly news, and also some confusing news that are surprising also. And in the end, we found that things are not all that bad because DisCo can be used to improve our disassemblers as well. So let's go one by one. Well, the good news is that disassemblers have complementary capabilities, and this is the main point on which the whole project leverages on, because disassemblers can be combined to form DisCo and DisCo is able to give superior disassembly performance because the different disassemblers have complementary capabilities. The bad news is that disassembler performance varies wildly and is very sensitive to architecture and compilation configurations. And we also found a bug in Ghidra during the course of our study. What is confusing is that relative ranking is not always straightforward or even consistent because it depends on what kind of metric you use to consider the performance. And in the end, we have also showed that DisCo can be used to improve other disassemblers. So there is still hope for all these disassemblers to improve. Okay, so the good news is that complementary capabilities of disassemblers is very good news because it means that if we combine them, we can get superior disassembly accuracy. So if you look at the Venn diagram on the right, we actually have taken a subset of MIPS binaries and we are using IDAPRO and Ghidra to actually find out if each one of the disassemblers can find function stars that the other one cannot find. And as you can see in the Venn diagram, it is showing that 7.3% of the actual function stars were identified only by IDAPRO correctly, and 10.7% of the function stars were identified correctly only by Ghidra. So this means that each one of the disassemblers are able to identify correct function stars which cannot be identified by the other one. So that means if we combine these disassemblers correctly, we can get a performance improvement. However, we also need to take note that each one of the disassemblers can also identify some false positives, and so if we combine them blindly, we will also get a lot more false positives as well. So combining the disassemblers has to be done very carefully. We want to also present some more information about our bug discovery in Ghidra. So we found that version 9.1 performs worse than the earlier version 9.0 for function star identification for ARM binaries. And in this slide, I'm showing you the ticket that we created, which includes the full report for the bug discovery. And the Ghidra team has actually tagged a bug label to our discovery, and they thanked us for the discovery. In our full report, you can also see that we have suggested a patch for this bug as well. So in this graph, I'm just showing you the extent of the bug, because in the graph on top, you can see that Ghidra 9.0 performs much better than Ghidra 9.1 for both the average as well as the 5PWC performance for all the different compilation options. So this is because version 9.1 had a misconfiguration in the function signature file, and this prevented correct function star identification in certain cases. That is why the function star identification is worse in version 9.1. And if you look at the link at the bottom of the slide, you will find the full description of the bug together with our suggested patch. Okay, in this slide, I just want to point out that performance actually varies within, even for a group of binaries that were compiled in the same way for a disassembler. So if you look at, let's say, BAP, you can see that from the table on the right, for the MIPS architecture, for binaries belonging to the MIPS architecture, for BAP, you can see that there is a huge range between the average performance and the 5PWC performance. And it's not just for BAP, there are also other disassemblers in which you can see a similar huge difference between the average and the 5PWC ranges. And even for Binary Ninja, which seems to be the best performing disassembler among these disassemblers, you can see that for the MIPS binaries that were compiled with Clang, there is still a difference of 8%. So we want to just point out that due to this range, it is sometimes hard for us to actually confidently say which is the best disassembler to use for a particular given binary, even if we know which compiler was used and which compilation options was used for that binary, which is itself hard to find out in the first place. Okay, in this table, we want to show that it is sometimes also confusing to decide on which is the better disassembler, because if you focus on Ghidra and IRA Pro, we can see that actually Ghidra outperforms IRA Pro by 5% for the average performance, but IRA Pro outperforms Ghidra by 8.3% for the 5 PWC performance. And what is surprising is that IRA Pro again outperformed Ghidra in 25.9% of the binaries by at least 10%, which is very significant. So given all this information, it is a bit hard to really say whether Ghidra is better than IRA Pro or IRA Pro is better than Ghidra for a given binary. And we notice a similar trend for some binaries between Binary Ninja and Anger as well. So the key message from this slide is that ranking disassemblers according to average or 5 PWC performance may actually lead to different rankings. And so it's hard to really say which disassembler is better than which other disassembler. And also, we notice that disassembler performance is sensitive to architecture, compiler, and compiler optimization levels. If you look at a table on the right, for example, for Anger, you can see that clearly Anger does better for the MIPS architecture than for the ARM architecture. If you look at the BAP disassembler, you find that for ARM binaries, it does way better when it's compiled with the GCC than compiled with Clang. And if you look at the bottom two graph, you notice that the performance for binaries compiled with the O3 option is worse for most of the disassemblers. In fact, for all of them, because there is a dip when it comes to the binaries that were compiled with the O3 option. So the key message here is that disassembler performance is affected by architecture, compiler, and compiler optimization levels. So in this table, we are actually showing you the RPI values, the relative performance improvement values for the different kinds of DisCo versions. We have, for example, we can combine all the 5 disassemblers for a DisCo all version, or just the free disassemblers for the DisCo free version, or just IRA Pro and Ghidra. But what we want you to notice here is that all the values are positive. That means the RPI or the relative performance improvement is always positive when you combine disassemblers. And this is because disassemblers inherently have complementary capabilities. So the main idea here is that if you combine disassemblers, you will get superior disassembly capability. And these tables give you a bit more detail. Here we are actually, the table on the left shows you the average F1 score performance for both MIPS and ARM binaries, and on the right this table shows you the average as well as 5 PWC performance for just the MIPS binaries. In both cases, you can see that DisCo All does the best because it provides you the good performance that is also stable across the different compilation configurations. And even when you compare it with Binary Ninja, you can see that Binary Ninja seems to do the best among the other disassemblers, but DisCo All provides a significant improvement of up to around 11%, especially for 5 PWC performance. So what we want to say here is that DisCo All can still outperform the other disassemblers, not only for the average scores but also for 5 PWC. So the main point is that when you combine disassemblers, you can get a good and stable performance regardless of the binary. However, if you use other disassemblers, like for example Binary Ninja, you might get a good performance on one binary that was compiled in a particular way, but for another binary that was compiled in the same way, you may not get the good result. So in general, combining more disassemblers gives stable and good results. We also mentioned that DisCo can be used to improve other disassemblers. So we tried this technique on Ghidra. The improved version of Ghidra is called Ghidra Plus, and we can do this because DisCo can generate function start signatures from training data, and these signatures can be incorporated into other disassemblers like Ghidra, for example. And we added these signatures into the function byte parent file in Ghidra, and the table shows the improvement between the Ghidra and Ghidra Plus. So you can see that Ghidra Plus actually gives us better and more consistent result compared to Ghidra. And also again, if you look at the table on the right, you can see that when we use Ghidra Plus, there is improvement of up to 18% for the 5 PwC scores. So again, we can see that Ghidra Plus is able to offer more stable and good performance. So in conclusion, in this work we have presented DisCo, which is implementing a very novel approach where we combine disassemblers instead of trying to find out the best disassembler. And we have shown that DisCo outperforms other disassemblers, and it can even be used to improve other disassemblers. And we have also showed that disassembly in the current state, disassembly is actually very brittle, because no single disassembler is able to dominate others for all configurations. And also performance is affected by the compilation options that are being used for a particular binary. With that, we have come to the end of the presentation. Thank you so much for listening to my presentation.